Pleasure to be here today to talk about integral abutment bridges. The AASHTO Committee on Bridges and Structures has a major push right now for workforce development. So this is a great opportunity for us to share information among our colleagues in the bridge industry on topics of interest. And this is definitely a topic of interest. We got quite a few people signed up for this, which is awesome. Again, today we're here to talk about design considerations for integral abutments in single-span steel bridges. My name is Michael Kulmo. I'm the Chief Bridge Engineer with CHA Consulting. We're an East Coast consulting firm. I've been designing bridges now, I just did the math, 41 years, 42 years, I'm sorry, 42 years I've been doing this. And so have a lot of experience designing integral abutment bridges. In our neck of the woods, we do an awful lot of integral bridges. And so it's my pleasure to talk about what I know about integral abutment bridges and what is going on in the country with regard to design of integral abutment bridges. Get my PowerPoint going. So the presentation today, the first thing we're going to talk about is what is the definition of an integral abutment? What does AASHTO say about that? We're going to talk about the benefits, and there are several significant benefits for integral abutments, where they're appropriate, where they're not appropriate, some of my thoughts on that, and then get into some design considerations for integral abutment bridges, specifically look at the AASHTO LRFD bridge design specifications, and then look at state DOT provisions, primarily focusing on Minnesota DOT. Then we'll show some common details, again, focusing primarily on Minnesota DOT. And then so we'll go through a couple example construction projects to show photos of how these things actually get built. So first, we're going to intro into integral abutments, talk about what they are and when they're appropriate. So this is the AASHTO LRFD bridge design specification definition for integral abutments. It states that integral abutments are rigidly attached to the superstructure and are supported on a spread footing or a deep foundation capable of permitting necessary horizontal movements. Interesting, it says spread footing. Most integral abutment bridges do not have spread footings, and there actually are some AASHTO provisions I'll share later with spread footings. My feeling is those are basically three-sided rigid frame structures where the vertical legs of the rigid frame are technically part of the abutment. And so it would be considered an integral abutment bridge as well. Most integral abutment bridges in the U.S. have deep foundations, usually a single line of piles, as I showed here in the diagram. The key features of an integral abutment bridge are the superstructures, like virtually every other superstructure. But the key thing is the superstructure is made integral with the stems of the abutments, forming the integral abutment frame. Wing walls are typically cantilevered off the back. We'll talk about that in detail today. We'll also talk a little bit about approach slabs and how they play into the design as well. Talk a little bit today about semi-integral abutments. There is no AASHTO definition for semi-integral abutments, but a lot of states build these structures. And generally, it's a bridge with an integral diaphragm at the end of the bridge that is attached to the superstructure. There's typically a joint below the beams. Sometimes it's directly below the beams. Sometimes it's a few feet below the beams. There's different details floating around out there. This particular detail is from Minnesota DOT. I like this detail a lot. But typically, semi-integral abutments have expansion bearings and fixed bearings underneath the beam to allow for thermal movement of the superstructure, but not in sync with the substructure below it. Typically, the substructure is more of a conventional abutment. And we'll talk a little bit about when these are appropriate and when you would want to go to a semi-integral design in a minute. So European experience. About 8 years ago, I went to a conference in Italy. It was a bridge conference, and they had a session on integral abutment bridges. And I was like, oh, this is great. I'm going to go and learn about what the Europeans are doing for integral abutments. And everyone thinks Europeans are way ahead of the U.S. and we're lagging behind. Well, the exact opposite is true. In my experience, the U.S. is very much ahead of the Europeans when it comes to integral abutments. A lot of the engineers from Western European countries didn't like the U.S. details. They get nervous about having a single line of piles and worried about the bridge is going to get out of position, that one side may push harder than the other side and the bridge won't be vertical. And they really don't, they weren't in favor of the U.S. style call of integral abutments with a single line of piles at the abutments. They considered a three-sided frame an integral abutment bridge. And technically, according to the AASHTO definition, they are. This is a photo of perhaps a three-sided concrete frame. In Europe, they would consider this an integral abutment, and technically in the US, you would also consider this an integral abutment because the abutment walls, the stems, are part of the superstructure, so it meets the definition. Interestingly, though, at that point, England was building US-style integral abutments. One of the presenters was from England, and he showed photos of designs in England that were very much similar to US, and he credited the US that they had taken the ideas from the US market and they were building US-style integral abutments in England at that time. Keep in mind, this was about 8 years ago. Things may have changed and evolved since then, but it was just at that snapshot in time, at least the conference that I attended, integral abutments were not as popular in Europe as they are in the US. So pile types, as I showed in the first couple slides, most integral abutment bridges have piles supporting the abutment stems, and typically a single row of piles. The most common type of pile used in the U.S. are H piles. Typically the orientation of the piles are in the weak direction with regard to thermal expansion and contraction of the bridge. In the photo to the right, you can see the center piles cut off, and you can see how it's oriented in the weak direction. Things get interesting when you get to skewed bridges. The question is, do you have the pile installed along the skew of the superstructure, or do you keep it square to the abutment? And the answer to that is I've seen both. It seems to be there's no standard approach to that. Either way seems to work just fine. So I suggest looking at whatever DOT you're working in, looking at their bridge manual for guidance. And really, you can't go wrong whichever way you do it. I would typically recommend having the pile oriented on the skew with the superstructure to correlate and correspond with the thermal expansion direction of the bridge. Drill shafts have been used in integral abutments, typically small diameter drill shafts. The problem with large diameter drill shafts is they get very stiff and they'll generate a lot of force when there's thermal expansion and contraction of the bridge. So we tend to see smaller drill shafts for integral abutments. Then a question comes up, I get this asked quite often, micropiles. Can we use micropiles for integral abutments? I'll cover that later. There are some issues with micropiles, or at least perceived issues that are being studied, and there's several studies ongoing right now with the use of micropiles for integral abutments. So what are the benefits? Why do we care about integral abutments? And there are some significant benefits. Number one in my book is the elimination of deck expansion joints at the end of the bridge. It's definitely a significant durability improvement. I like the comment, the best joint is no joint in the bridge. Because as we all know, bridge joints can be the number one cause of bridge deterioration, leaking deck joints, I should say. And I'm not taking a shot at the joint manufacturers. It's a very difficult thing to design a deck expansion joint that can last a long time and not leak. The abuse these joints take is brutal, and they tend to hold up for 10, maybe 15 years, and they start to leak. So if we can eliminate the deck joint, we're definitely going to improve the durability of the structure. And we're all looking for improved durability. We're in search of that 75 to 150 year service life. Elimination of bearings. Integral abutments don't require expansion bearings. Sometimes we use temporary bearings just to get the bridge built, but once the integral abutment is made and the connection is made to the superstructure, there is no need for bearings. The thermal movement is accommodated by flexing of the piles. So it's definitely an advantage not having bearings that you either, one, have to install, and two, have to maintain over the life of the bridge. So very low maintenance costs on these structures. Next item is lower cost. We're already eliminated bearings and we eliminated a deck expansion joint. Okay, we're also going to use fewer piles. When compared to a typical pile-supported cantilever abutment, which might have 20, 30 piles in the abutment, we're looking at four to six piles in a typical integral abutment. So significantly fewer piles, which saves money. There's no footings, so we're not pouring a footing. And so it's another step in the construction process, which is going to save quite a bit of time. And then the last bullet I have on here is less excavation. We're digging down quite a bit less than we would with a conventional abutment. And the key thing I highlighted is typically the excavation is above water line. So we could build these bridges without cofferdams, without pumping water, and which greatly reduces the amount of time to build the bridge and also reduce the cost to build the bridge. And I'll show some photos of an integral abutment bridge where you'll see that the entire construction of the abutment was done above the water table. So the benefits for the superstructure, we're gonna get some benefit there. We're gonna get some help there. The answer is not really. Designers typically neglect the stiffness of integral abutments because the stiffness of the piles is significantly lower than the stiffness of the superstructure. It's a decimal point in the equation. So we typically we don't take advantage of the stiffness. I'll talk a little bit about the AASHTO provisions for certain types of bridges where you may want to consider the forces from the integral abutment, but typically we neglect the forces, especially the compression forces in the superstructure, due to the soil forces acting on the abutments. And the reason for that is just that the forces in the superstructure are peanuts compared to the bending moments that we have from truck passage, for instance. So where are they appropriate and where are they not appropriate? Single span bridges, definitely. You should be looking at integral abutments for virtually every single span bridge you're designing. You can definitely do it with continuous bridges. It's been done in certain states. This presentation is really focusing on single span, but it can be done with multi-span bridges as well. A question comes up a lot is what are the maximum length of bridge between integral abutments? And the answer is it depends on where you're at. Every state has different requirements. Some states have requirements around 150 feet max. You'll see later in this presentation, Minnesota DOT goes to 300 feet, and Tennessee DOT, I know, goes even longer. So I suggest you look at the bridge manuals in these states to get an idea of how long you can go with the design of an integral abutment bridge. So where are they not appropriate? We have found with shallow bedrock, you have issues with the piles. If bedrock is only down, say, 20 feet below the road, you really cannot achieve pile fixity in such a short distance. Some states like Massachusetts will core the piles into bedrock. They call it a rock socket, and that's one approach. But typically with shallow bedrock, you want to shy away from integral abutments because there can be some issues. In that case, though, that's where you might look at a semi-integral abutment. Might be an appropriate solution for that situation. This is the next one, bridges with significant scour. It's a debatable topic. I've asked several DOTs this question is, are you okay with the soil behind the abutment being scoured away in a major flood event? I've seen pictures of bridges after floods where the entire backfill was gone, where the river essentially scoured out behind the abutment and the bridge was fine, and they just backfilled and reopened the bridge. But you're losing the road. So it really is debatable whether a DOT is going to require scour design. Again, I would look into the bridge manuals in the states and see what they require. I know for a fact that Connecticut DOT has requirements for depth of stem for integral abutments. And then for long bridges, for very long bridges, the soil pressures brought on by thermal expansion of the bridge can get significant. You're putting significant flexure in the piles. So a lot of the states limit the length of bridge for these reasons. So now we'll get into the design requirements for integral abutments. And there is, at least as far as I'm concerned, there is no national design process for integral abutments. We use engineering judgment in most cases. AASHTO, I'm going to go through the AASHTO bridge design specification criteria for integral abutments, and there's not much. There's a few things in there. But there are some states that have some significant design requirements, such as Massachusetts and Minnesota. I'm sure there's more out there. Tennessee, I know, has a lot of requirements as well. Again, refer to the bridge design manuals in these states if you're designing an integral abutment there. So let's dive into the AASHTO LRFD. I did a search of integral abutment in the actual LRFD bridge design specification, and about 10 hits came up, and I'll go through each one of those now. This is the first thing, Article 2526 on deformations says that elastic vertical, lateral, and rotational deflections due to applicable load combinations shall be considered to ensure safety, satisfactory service performance of bearings, joints, integral abutments, and piers. And it just basically says that we have to design or we have to consider the movements of the bridge in the design of the structure. Article 311.5 is on the loading section. The earth pressure loading has a comment there. It says that for integral abutment walls, significant arching of the backfill against the wall does not occur, probably due to the movement of the structure, and the resulting lateral load due to earth pressure acts at a height of h/3 above the base of the wall. And furthermore, you could read what goes on beyond that. So there are some guidance there on how to handle earth pressure on integral abutment bridges using this provision. Section Article 4.6.1, influence of plan geometry, is really looking at structures curved in plan. Now, a lot of states do not allow integral abutment bridges for curved bridges, or if you have significantly curved bridges. But it says here that the substructure shall also be considered in the case of integral abutments piers are bents. So consider is a key word. It doesn't say you have to do it, but it says you should consider it. As I said before, most engineers neglect the stiffness of the piles. Some consider the bending moments caused by the soil pressures acting on the back wall and the stem, causing negative bending forces in the superstructure when you have thermal expansion. I'll show that in a minute. And there are provisions in AASHTO that hint that maybe that's something you want to consider as well, which I'll get to in a minute. For curved steel bridges, Article 46333, this paragraph is in the commentary. The stiffness of supports, including lateral restraints, such as integral abutments or integral piers, should be recognized in the analysis. Keyword is should, doesn't say shall. Since bearing restraint is offset from the neutral axis of the girders, large lateral forces at the bearings often occur and may create significant bending in the girders, which may lead to lower girder moments than would be computed if restraints were not present. The engineer should, again, should ascertain that any such benefit recognized in the design will be present throughout the useful life of the bridge. And this has to do with the soil forces pushing on the integral abutment, causing negative bending at the abutment. Now, that negative bending can reduce your positive bending along the span, and that's what this commentary is hinting at. But the key word here is a lot of shoulds here, not shalls. I say you may want to consider it, but I would just say, be careful. Most engineers would not take those forces and say, well, I'm going to reduce my live load bending moments because I have the soil pressure pushing on the back of the abutment. And the reason why you wouldn't want to do that is if the bridge contracts, you lose that soil pressure, and it's not present all the time. So it's something you really can't count on. Okay, now we get to section 11 in the AASHTO LRFD, which covers abutments, walls, and piers. And here's where we find the definition of an integral abutment, which I shared earlier in one of the earlier slides. We actually have an article on integral abutment bridges, Article 11613. It just says that the abutment shall be designed to resist and or absorb creep, shrinkage, and thermal deformations of the superstructure. So the thermal is probably the more important one of all the three. Then I circled this one area. To avoid water intrusion behind the abutment, the approach slab should be connected directly to the abutment, not to the wing walls, and appropriate provision should be made to provide drainage for any entrapped water. I mean, that's a good idea for any abutment to have drainage behind the abutment, but specifically for integral abutments, AASHTO tells us to, one, use approach slabs, and two, put some drainage to drain the soil behind the abutment. One thing it doesn't mention about the approach slabs is that it also reduces the surcharge loading on the abutment stem by pushing that live load further away from the back of the abutment. So in the Article 11654, there are provisions here for seismic earth pressures on bridges, and there's some text in the commentary for integral abutments. I won't go into a lot of detail on this thing. It's a fairly large article with a lot of text, but there are some provisions, some recommendations for how to handle seismic earth pressures for integral abutments. So that's it for the AASHTO LRFD code. That's what we have. And you'll notice there's not a lot of equations. There's not a lot of specific requirements. And that's why I said before, engineering judgment primarily is what's used. So now talk about how do we typically design these bridges. And as I mentioned before, we typically treat these bridges as simple spans. And we neglect the stiffness of the piles. And in most cases, neglect the soil forces acting on the abutments when we design the beams. So what's good about this is when you're designing your girders and your beams, you can use standard design software, treat it as a simple span, and design it. It's conservative because, like I said before, the soil forces tend to reduce your positive moments, but we don't count on those soil forces to reduce positive moments. So the good news is if you're designing a simple span bridge, you want to use the Short Span Steel Bridge Alliance E-Span 140, you can go ahead and use it for an integral abutment bridge. Any software you use for design would work with integral abutments. Which is a nice thing. It's not a special design requirement. And again, we neglect the stiffness of the piles because if you calculate the moment of inertia of that pile group compared to the moment of inertia of the superstructure, it's a decimal point on the end of the equation. So it's not even worth considering. Here's a diagram showing the earth pressure. When the bridge expands, you get half the movement, half the expansion occurs at each abutment. And that creates passive earth pressure. When the bridge is contracting, we get active earth pressure. So we have two different loadings, and it can generate, I have the arrows pointing where the pressure is being applied, the centroid of the pressure is being applied, and it does result in negative bending in the superstructure. We typically, we can check that negative bending. We would just design your the bending moment at the abutment, design it like you would for a continuous steel girder in negative bending at a pier. You would check to make sure there's adequate deck reinforcement to control cracking. But here's the key thing, and this is a steel bridge webinar. Uh, this issue is more of an issue with pre-stressed concrete girders, because if you design any pre-stressed concrete girders, you know there's a lot of tension or very high stresses at the top of the beam at the abutments. Adding a big negative moment on the end of a beam can be problematic with pre-stressed concrete. So you have to be very careful with pre-stressed concrete. But the good news is steel structures can easily handle these negative moments. It's not a problem at all. It's something that I suggest you check, again, similar to a negative moment region of a continuous girder. Important thing to understand, and I've seen this mistake made a few times, is consider the sequence of construction and include notes in the plans to specify the sequence of construction. And they're really, when you go to pour the deck and the integral diaphragm, there's really three areas that are poured. You got the integral diaphragms in each end of the bridge and the deck over the top. You really need to allow, you want to pour the deck first. So the red region would be poured first. And what that does is allows the girder to deflect under dead load, and your beam end rotations occur before you make the bridge integral. And then you go and pour the abutment diaphragms after the deck. Now you can pour the second abutment diaphragm with the deck. So you say you start on the left side of the bridge, you work your way across. At the end, when you hit the end of the red section, you can go ahead and pour the integral diaphragm as a continuous pour with the deck. But then you have to come back and pour the integral diaphragm at the other end of the bridge, because you want to have that rotation take place before you make that connection. You could consider retarding the concrete, although I would not recommend it. I've seen cases where with beam end rotations, you can get plastic cracking in that diaphragm before the concrete even sets. So I really consider, I would suggest you include notes in the plans noting this type of sequence of deck pours. So now we're going to get into state DOT provisions. What do the DOTs say? As I mentioned before, AASHTO doesn't have a lot of provisions, and some states have significant provisions, which is helpful. Unfortunately, every state seems to treat these a little bit differently. So us as bridge engineers who work in multiple states have to make sure we read the provisions and make sure we're following what the states are specifying. So several states do have design provisions in the bridge manuals. Again, Mass DOT I'm familiar with. They've had provisions for many years. They have standard rebar detailing, standard pile designs. Things are pretty well standardized in Massachusetts. They've been building integral abutment bridges from almost my entire career, like other states like Tennessee as well. But today I want to focus on Minnesota DOT. It's a Minnesota webinar, and Minnesota DOT has a very good bridge manual with some very good practical approaches for designing integral abutment bridges in Minnesota. So let's dive in. So in the abutment type selection portion of the Minnesota Bridge Design Manual, it covers integral abutment bridges, and it's got some very practical approaches for selecting when to use integral abutment bridges. For instance, if you read the bullets there, bridge length, you can go up to 300 feet if you've got low skew. That's between abutments. And the expansion length at the abutments is 150 feet, again, 1/2 on each end of the bridge. If you start getting into skewed bridges between 20 and 45 degrees, you can the bridge length is limited to 100 feet because of the skew effects. And one of the issues with skew, there have been concerns, I call it the snowplow effect. If you take an integral abutment that's on a skew and you push it into the soil, thermal expansion, that you will get a transverse component to the resultant forces acting on the abutment, which could lead the abutment to shift to the right or left, depending on the skew. Like a snowplow, it wants to, you have a resultant force that's transverse. And for that reason, many states limit skew and integral abutments. I believe Vermont Agency of Transportation did a study years ago on skewed bridges. I think UMass Amherst did the work. And I recall it wasn't as significant as it was concerned, but still most states do a limit skew on integral abutments. For bridge lengths between 100 and 300 feet with skew that's greater than 20 degrees, there's a linear interpolation between those two for the acceptable bridge length for integral abutments. It does note here, the second bullet's interesting, that for bridges with cast-in-place piling for the abutments, this length is limited to 150 feet. That's probably due to the stiffness and concern about cracking of those. Next bullet talks about horizontal alignment. Slight curvature is allowed, but it's considered on a case-by-case basis. The next bullet covers cantilever wing walls. I'll show a diagram of that in a little bit. And the key thing is the integral abutment wing walls do not tie into the roadway retaining walls. We have to allow the bridge to expand and contract thermally and the ends of the bridge to rotate with live load. So we got to make sure we have a disconnect between those. And this next bullet covers some of the front face exposure limits. I have a diagram I can show later. And then beam depths are limited to 72 inches. This is a diagram. It's in the Minnesota Bridge Manual that graphically shows those first couple bullets as far as bridge length in regard to skew. So just a little table you can quickly go to as opposed to doing the calculations, which are not very complicated. This provision talks about semi-integral abutments in Minnesota, and it talks about where they are applicable. When the wing wall length cannot be met, the requirements for structure depth, superstructure depth, and wing walls cannot be met, you should go to semi-integral. And then again, bridge length, there are requirements there as well for bridge length. There are, Minnesota has details, and this is similar to a lot of states showing details as far as depth of embedment of the integral abutment into the abutment slopes. In this case here, the recommended minimum thickness is 3 feet below the stem, and they're proposing to put riprap for scour protection in front of that. And then there's notes about skewed bridges as well. They make a note that the typical Minnesota requirement of a 4-foot 6-inch embedment below grade is not required for integral abutments, like you would with a cantilever abutment. And then it specifically states that the H-piles should be oriented in the weak axis bending with regard to longitudinal bridge movements. Minimum pile penetration into the stem. This varies state by state. 2'6" is about average. I've seen up to 5 feet, and I've seen less than 2 feet. My experience, 2 feet is plenty of embedment. 2'6" is very good, and you can develop the full bending moment capacity of the pile in 2'6". Even 2 feet, you can do that in my experience. Then there's a note about avoid using 16-inch cast-in-place piles or 14-inch HP piles. Again, trying to keep it relatively flexible to accommodate the thermal expansion and contraction. So the Minnesota Bridge Manual has details for wing walls, saying the maximum length of the cantilever wing wall is 14 feet. And I've seen in some cases where engineers want to put piles underneath the wing walls. You should not do that because that wing wall is rotating with the integral abutment with live load. And you don't want to have any piles underneath the wing walls. It's rotating with that abutment stem. So it's a cantilever. I call it it's like an elephant ear, we call it. It sticks out the back. And Minnesota limits the length of that to 14 feet, which is about average. Most states vary between, say, 10 and 15, maybe even 20 feet. But 14 is a pretty good average that's used. Now we get into details. These are the typical details from Minnesota DOT. I like these details. They're similar to most states that do these. Some minor changes you'll see later. I'll show some details of a Massachusetts integral abutment. But a couple of the features, I circled the temporary bearings. That underneath the girder, when you erect the girder, Minnesota DOT recommends a fairly thin half-inch a half-inch by 12-inch by 24-inch bearing pad, which really is not an expansion bearing. It's just a pad to eliminate point loads on the concrete below. And that's to allow the beam to rotate when you're casting the deck, but it's really not there for any structural purpose at all. Because once the integral abutment connection is made, the bearing doesn't do anything. Also looking at the polystyrene on the front face, underneath the bottom flange, on the front face of the abutment. Several states use details like this, although some do not. It kind of varies. I believe there have been some issues with cracking in the past underneath that area. So some states require the polystyrene underneath the bottom flange. Again, it's not to allow for live load rotation. It's really just for construction to avoid potential cracking. Moving on, additional criteria in the Minnesota Bridge Manual. I like this criteria. It's an interesting one that is debatable in the industry, saying that design the piling for axial loads only. We know there's going to be bending in the piles, especially when there's live load on the bridge, and also when there is thermal expansion and contraction. But this kind of provision came out of, I believe, Tennessee. And it's a revision that I believe in. And you might say, but there is bending in the piles. Well, I'll cover that in the next slide. My theory of why you can ignore bending in the piles and just design them for pure axial load and ignore bending. Also provisions in this particular section of the bridge manual talking about live load distribution and how you essentially treat the pile cap, the abutment stem as a pile cap, and you distribute the live load along that using simple logic, nothing very complicated. So let's talk about this flexure issue. And Minnesota only specifies axial load. So we ignore bending in the piles. States like Massachusetts does not. We do design piles for flexure in Massachusetts. And I believe in Tennessee, they also ignore bending in the piles. They just limit well, like Minnesota, they limit the length, the maximum length of integral abutment bridges. So they've done studies based on typical loads in piles and typical thermal bending moments in piles and determined that as long as you stay within the limits in the bridge manual, you could ignore bending. So why not flexure? These are my thoughts. There's nothing in AASHTO, nothing published that I'm aware of why we do this. But in my eyes, we can consider flexural stresses to be similar to residual stresses in steel. And the reality is structural steel, and I got this diagram off the internet, all rolled sections have significant residual stresses. 10 to 15 KSI is pretty standard. And that's just due to the rolling process and the cooling of the steel in the mill. So we ignore residual stresses in design. We just go through and design it. So why do we ignore these high 10 to 15 KSI residual stresses? And this might be the answer on why we can ignore bending stresses in piles of integral abutment bridges, because it's really similar to a residual stress. So let's take a look at that. And when I was in grad school, my professor taught us, we studied residual stresses in the design of columns. And why do we ignore residual stresses in columns? And the idea is that as you apply compression, your compression in the column is additive to the residual compression stress in the beam. So that area of the beam will yield before the other areas of the beam. But as you continue to add load to the beam, that eventually you start yielding the compression area, but now you've got ample capacity on the tension side of the beam where you haven't even come close to yield, and you've got ample capacity. And the result is the ultimate compressive load works out to be ASFY. And that's if you have a compact section. So you literally, we ignore residual stresses, and that may explain why we as engineers might feel comfortable ignoring the bending stresses in integral abutment piles. Minnesota DOT has some geotechnical requirements, fairly straightforward. The key thing is they design for full passive earth pressure. Massachusetts DOT does a calculation based on the amount of thermal movement to see if you get to full passive or you get to partial passive. So there are different provisions out there. Again, refer to the your bridge manual. But I reiterate here, this may be an issue with pre-stressed concrete beams having a significant negative bending moment at the ends, but steel can definitely handle it, and it's really not a big issue. As far as semi-integral abutments go, Minnesota DOT has some great details. I like these details a lot. I've seen various details around the country. The key thing is the bearings are designed to accommodate thermal movement, but the longitudinal forces, such as braking forces, are resisted by the back wall. So it really helps out with dealing with those longitudinal forces. And I added on here, this detail works really well with accelerated bridge construction. I'm going to show you some details of that are used in Utah, and we've used them in other states as well, where this design, you could design a semi-integral bridge with ABC. So you get the benefits of integral bridges, and you also get the benefits of accelerated construction. And here's what that might look like. This is a bridge in Rhode Island that our firm designed a few years ago. Single span steel bridge, about 80 feet. And the detail on the right is a SketchUp model of what it looks like, what the semi-integral abutment diaphragm looks like. And you notice that tooth on the back, which looks a lot like the Minnesota tooth. And those other knobs sticking down are used for sliding the bridge. It's a great detail that works really well. And here's how it goes. You build the bridge on temporary supports nearby. Once the abutment is finished, you start sliding the bridge over on temporary slide bearings or a slide track. Once it's in place, you jack the bridge up, put the permanent bearings underneath those shoes, and then you place, we typically use closed cell elastomer to seal off that joint in the back to prevent groundwater from coming onto the bridge seat. Very simple detail. This can be used for lateral slides, it can be used for SPMT moves, and it can be used for modular deck beams as well. All ABC methods that are very much applicable to steel bridges. So now let's go through some sample projects. Let's take a look at some bridges that are actually been built. And I just got two I want to share, primarily because I have a bunch of photos. I have one bridge with just one photo, but then I have a really nice steel bridge with a bunch of photos during construction. So I mentioned before about micropiles, and there's been a lot of discussion on why can't we use micropiles for integral abutments. And Massachusetts DOT is studying this right now. This is the Champeau Road Bridge in Sturbridge, Massachusetts. It's about a 65, 70-foot long bridge. And Mass DOT had a desire to use micropiles, but we took a conservative approach. And the concern with micropiles, if you look at the photo on the lower right, it shows your typical micropile piece, and you'll notice there are threads cut into the ends of the piece. So as you install a micropile, you're actually connecting the pipe sections with a threaded connection. Well, the concern over the threads is at the top of the splice, you have threads that are essentially exposed and that are subject to potentially significant bending. And the concern is that you can maybe fracture that pipe because you have a notch essentially at the top of the coupler. So that is a concern. So for the design of this particular bridge, we specified a minimum coupler depth. The coupler had to be X number of feet below grade, where the bending moments in the pile were not very significant. So it is a concern, but Massachusetts is looking at this. We've installed a ton of gauges on this bridge, and we are monitoring this bridge now. It's been in service for a little less than a year, and we'll continue to monitor it for a few more years. And we're actually building a second bridge in central Massachusetts with the same details. In addition, though, University of Maine is studying this as well. They're actually doing laboratory testing on these couplers and these connections to see if this is a problem or a perceived problem or a real problem. So more to come on that and integral abutments with micropiles. So now we'll get to an example project showing the construction of an integral abutment bridge. This is a bridge in Putnam, Connecticut. It is slightly longer than your short span steel bridge. This is a short span steel bridge alliance webinar, but all the details and all the photos shown in this are applicable to any steel bridge. And I picked this one again because I have a lot of good pictures of this bridge under construction. This particular bridge had a 200-foot single span, which is a pretty long single span, but it was very advantageous to span this entire river because of environmental regulations and scour concerns. So this thing is a 200-foot single span with full integral abutments. So this is a layout of the bridge. It's a brand new road, which is nice. We don't have stage construction to deal with here. It was the land that the industrial park was being built on. It was a former landfill being converted into a technology park. And we came up with a new entrance road. The existing access to the site was actually a temporary bridge, an AASHTO temporary bridge. And the idea was they wanted to have a permanent bridge to access this park. And you'll see we squared everything up really nicely, 200-foot bridge with zero skew. Cross section of the bridge, which is just your typical steel bridge. We have four girders with a composite concrete deck. In Connecticut, we use a lot of asphalt overlays with high quality membranes, waterproofing membranes, and the lower detail shows the elevation of the bridge. As far as the pile layout, we went with the layout here, having the piles in the weak direction. As you from the previous slide, you saw we had four girders. A lot of times, engineers will put the same number of piles as girders. So if you have four girders, you go with four piles, and that's a good design because you place the pile directly underneath the beam. Now, I have seen details where engineers actually had the pile supporting the erected beam and then casting concrete around the whole thing. I don't recommend that. It can get problematic for how do you get the elevations right and make that temporary connection. Most people will pour the integral abutment stem and then set the girders on top, like the Minnesota details. In this particular case, we went with six piles. And the reason for the six piles was the span length, at 200 feet. We were using the Massachusetts DOT design requirements, so we actually were calculating bending stresses in the piles. And to control the stresses in these piles, we went to a slightly larger pile, 14 by 102, and we oriented in the weak direction, but we used six piles as opposed to four. So this is a detailed abutment, should look very similar to the Minnesota details. I have a couple arrows pointing to a few things. One, the temporary erection pad, 3/8 by 24 by 10, very similar to the Minnesota details. Connecticut or Massachusetts does not require the polystyrene underneath the bottom flange. We've done it that way for years. It works fine. The embedment of the stem, 36 inches. That is I believe, Massachusetts requirement. That seems to work well. Again, similar to the Minnesota detail, or the same, I think. And then the embedment of the pile is 2 feet. Minnesota goes 2'6". This particular one was 2 feet. I'm okay with 2 feet. 2'6", I'm okay with that too. It's not a big issue to have that be 2, 3, or even 4 feet. As far as the reinforcing in the stem, you'll notice there's quite a bit more reinforcing here when compared to Minnesota details. Massachusetts does add quite a few shear bars as well into these abutments. You'll see those in the cross section. But I highlighted that the vertical bars, number 8's at 8 inches. That's because the significant bending moments acting on the stem are bending with the primary reinforcing picking that up as the vertical bars. So they can get quite large. Number 8's at 8. In between the beams, and number 8's at 12. Number 8's at 8 under the flange, and number 8's at 12 between the beams. I got photos to show all this later. Interesting detail we use for the temporary bearing. Again, similar to Minnesota details. Fairly thin elastomeric pad. It's just that we called it an erection pad. But you notice that the bearing stiffener, we moved it back a little. And it's because when the beam is erected with camber, primarily the beam is going to be sitting on that back corner. So we actually moved the bearing stiffener back a little, because once the concrete is poured, then the bearing stiffener doesn't even do anything anymore. The whole thing is encased in concrete, and it's just a temporary bearing stiffener. So we offset it slightly from the center line of bearing. Okay, details of the wing walls at the end, the flying wing walls. The section B is shown on the left. That is a cross section through the wing wall. And you'll notice the main reinforcing, number 6 is at 6, are the horizontal bars. It's designed as a horizontal cantilever or elephant ear. So your main steel is running horizontal. As far as I put an arrow pointing this structure at the end, that's called a highway guard transition. That is a transition between the beam rail approaching the bridge and the railing on the bridge. And the key thing is those two are separated by a 1-inch joint that allows thermal expansion of the bridge and end rotation of the integral abutment, keeping it separate from that transition piece at the end. Now we get into construction photos. It's a fairly straightforward construction. Being a long span steel girder, the contractor built temporary bents to support the steel and before the bolted splices were installed. But notice there are no cofferdams, nothing's being done in the water, and very simple construction, excavation up the slope behind the edge of the river. We showed this picture before, pile installation. Again, I put the arrow pointing at the dirt. We're way above waterline here. Very simple construction, easy, no dewatering. We're working in the dry, which is a real benefit. At the completion of steel erection, here's what it looked like. I just point one thing on here. At the ends of the beam, this is a weathering steel bridge. We do recommend, and the steel industry does recommend, you consider painting the ends of the beam because you can get condensation at the interface between the steel girder and the integral abutment bent. Although we did a study for Connecticut DOT and didn't find that to be a problem, but to be conservative, if you want to, you can paint the ends of the beam. Although, like I said before, I don't think it's that important because it doesn't seem to be an issue. Showing the construction of the end diaphragm, you see the beams are all erected, the temporary cross frames are in at the end, and the rebar coming out of the stem. Back up. Okay, notice there's holes in the web of the girder where reinforcing bars are passed through the girders to complete the reinforcing in the integral diaphragm. Showing the back end of the beams, showing the bars coming out of the abutment. You notice those 2 bars that are bent. That was so the contractor could tighten the bolts on the cross frames. Those bars were straightened out after the cross frames were installed. Good shot here showing the temporary bearing that the beam is sitting on. And that's it. So in conclusion, I truly believe that integral abutments should be your first choice for abutment substructures on steel bridges. You eliminate deck expansion joints, you're eliminating bearings, lower cost, easier construction in the dry, easier to get permits. It's just it has all the benefits that you would want in a bridge. And they are ideal for steel bridges. The negative moments that can be generated at the integral abutments due to passive earth pressure can be significant. Steel bridges can handle it. Concrete bridges, you've got to be careful. You can easily crack a concrete girder if you're not careful. Various pile types can be used. Most people use steel H piles oriented in the weak direction. That is the most popular choice. The AASHTO LRFD bridge specs have limited design requirements. There's a handful of requirements in there, but luckily some owners have some significant design requirements. And if you're in a state that doesn't have any requirements, I like the Minnesota DOT Bridge Manual. I think they have a very practical approach to integral abutment design with that. So with that, that concludes my presentation. I'll be happy to take any questions you might have now.